All right, welcome to the Explainer. Today, we're jumping into what might be one of the biggest shakeups in AI hardware we've seen in a long, long time. So, a company called Groq just kind of showed up out of the blue and started posting these performance numbers that, well, they just lit up the internet. The speeds they were showing off, they seemed frankly impossible.
And look, we're not talking about some tiny incremental improvement here. We are talking about an order of magnitude. That's about 10 times faster, 10, than the best of the best, the top of the line GPUs when it comes to spitting out AI responses.
But here's the kicker. This is the part that just doesn't make sense at first glance, and it's the puzzle we're going to solve together today. Groq did all of this using older, simpler, you could even say less advanced technology. So how in the world is that even possible? Okay, so let's get into it. Let's peel back the layers and figure out the secrets behind this mind-boggling speed. Because this is a story about being smarter, not just stronger. And this right here really tells the whole story, doesn't it? It's a classic David versus Goliath situation. You've got NVIDIA's H100, the king of the hill, built on this crazy advanced 4-nanometer tech. And then you've got Groq's LPU, built on 14-nanometer tech. That's like 3 generations behind. And get this, it doesn't even have that special super-fast memory, HBM, that GPUs absolutely need to feed their hungry cores. On paper, this shouldn't even be a contest. So that brings us to secret number 1. How does Groq pull this off? Well, it's not about brute force, cramming more transistors onto a chip. It's about a totally different way of thinking, a philosophy that's all about one thing: predictability. And this slide just nails the core difference. A GPU, you see, is non-deterministic. It's got all these layers of memory called caches, and it's constantly guessing where the data it needs is going to be. And every time it guesses wrong, you get a delay. Groq's chip, what they call an LPU, is the exact opposite. It's 100% deterministic. It knows. It doesn't guess. It knows the exact location of every single piece of data at every single moment. No guesswork, no delays. Yeah, that idea is called determinism. And what it means is that every single thing the chip does is perfectly planned out ahead of time by the software. There are no surprises, no waiting around, no wasted clock cycles. The whole thing just runs like a perfect Swiss watch, an efficiency that you just can't get when you're constantly guessing. Okay, so that's the chip itself. Now let's talk about secret number 2, because having a fast chip is totally useless if the connections between them are slow and clogged up. And Groq took that same idea of predictability and applied it to the whole network. Think about how GPUs are normally connected. It's kind of like a messy city grid, you know? It's full of traffic lights, intersections, and routers. Every little packet of data is like a car, making its own decisions, and what happens? You get traffic jams, you get congestion. It's totally unpredictable. But Groq's network, it's like a city with no traffic lights at all. Imagine that. A city where every single car's route, its departure time, even its speed, is all pre-calculated by some master computer to make sure there are 0 collisions. That's exactly how Groq moves data around. It's a perfectly choreographed ballet of information. And the result? Well, you can see it right here. It's just a massive, massive difference in efficiency. When you're doing AI inference, getting the AI to actually generate a response, you're sending lots of small data packets. In that scenario, GPUs might only be using like 15% of their available network bandwidth because of all that traffic jam overhead. Groq, they're using around 95% of theirs. It's just insanely efficient, almost no waste. So, when a GPU has to send data, it has to go through this whole checklist. Talk to the special memory, negotiate with a network card, navigate all the switches, wait for a signal back. It's a whole process. Groq just gets rid of all of that. All that communication overhead that just bogs down GPU systems, gone. Every single nanosecond is spent doing actual useful work. All right, so what happens when you take that perfectly predictable chip and you combine it with that totally congestion-free network? Well, you get something completely new. Think of it as the third piece of this puzzle. A true assembly line for AI. And I love this quote from Groq's head of silicon. He says, they haven't just built a better workshop, where a master craftsman carefully builds one thing at a time. No, they've built a hyper-efficient factory, a perfectly timed assembly line that's designed to do one thing and one thing only: crank out AI tokens, the little building blocks of language, at a truly insane speed. So really, it all comes down to these four interconnected superpowers working together. You've got the predictable chip, the software scheduled network with zero bottlenecks. You have this perfect synchronization where all the chips act like one giant brain. And finally, an ultra-fast internal design that gets data from A to B in the quickest way possible. And you know what? The payoff isn't just raw speed. All that efficiency, getting rid of all that waiting and waste, it also makes the whole system about 10 times more power efficient. They're saving a ridiculous amount of energy for every single token they generate. Okay, so let's pull back for a second. What does all of this actually mean for the future of AI? This isn't just another company making a fast chip. This is a potential new blueprint for computing. It's a fundamental shift in how we even think about designing hardware. I mean, think about it. For 25 years, the whole industry has been using an architecture, the GPU, that was originally designed to play video games. We've just been adapting it for AI. What Groq did was start with a totally clean slate. They asked, what's the best possible way to build a chip specifically for these big AI language models, and built that from the ground up. And here's the part that really blows my mind. They're just getting started. All of this incredible, record-shattering performance is on old 14 nanometer technology. They've already got a modern 4 nanometer chip in the pipeline. Can you imagine the leap in performance that's coming next? Which really leaves us with one final big question to chew on. If a 25-year-old architecture that literally powers our entire digital world can be so radically improved just by rethinking the problem from scratch, what other huge fundamental assumptions are we making in technology that are just sitting there, waiting to be completely overturned?